I'm very happy to introduce Professor Basudeb Dasgupta from TIFR. He's a professor at DDT at Research, and I could call myself privileged to have worked with him during my postdoc days. He did his PhD from TIFR. After that, he went to Munich and then Ohio and then TSK before he joined as a faculty at Tata Institute. And as I was saying, I was very privileged to have spent a lot of time with him. Not only the physics that I do is I owe to him, but also, he's also responsible for me knowing how to enjoy coffee. And by association, many of you know. So yeah, I'm very happy to give the floor to Basu. Yeah, please.
Thanks. Thanks, Bhavesh. Thanks for pleasant introduction. I think this is the first time I've been recognized for my achievements in coffee appreciation. I value it. Okay, thank you for having me. It's my first time here at BITS Pilani. Yeah. Okay, so I'll over the next 45 minutes or so, I'll want to tell you a little bit about actually fairly technical stuff. Okay, so this is not like just storytelling. There will be a bit of that, but this is fairly technical stuff. This is intentional because I get a lot of emails from people from BITS Pilani wanting to do projects. So you should know what you actually have to do if you are going to try to do physics. Okay, so let's start. So the talk has 3 punchlines. Having movies in 8 chapters is popular these days. I don't know how many of you got that. Not too many laughs. No. So there are 3 short chapters which are the precise results in the talk. So that's the feeding, fading, falling. Although the order in which they will appear in the talk are fading, feeding, falling. So the big picture is this. I'm guessing most of you have heard about dark matter. If you have not, I'll tell you a little bit about it. But the idea is that there is something called dark matter. It's an exciting field of frontier particle astrophysics research. And since about the 80s, seems like probably prehistory to many of you, but 1980s isn't that long ago. So it's for the last 40 years or so, there's been work going on in dark matter. But for the last 10 years or so, there has been this totally, crazy level of excitement about something else, which is, black holes and gravitational waves. Now, the purpose of this talk is to try to show how contemporary modern day dark matter research, which is not a new subject, has made contact with this very exciting field, and what new stuff is happening in dark matter research that is very strongly informed by the growing interest and the activity in gravitational waves and black holes. So all the 3 things that I'll tell you about basically look at this interface between dark matter and black holes and gravitational waves. So there's a lot more to say about dark matter. It's a huge field. There's a lot more to say about black holes and gravitational waves and so on. We can't go into all of that. My purpose here is very, very narrow. That I want to kind of shine a little bit of light on a very small part of the big picture of astroparticle physics research on this interface between dark matter physics and black holes and gravitational waves. But by doing so, by being so specific and thinking about something very, very particular and technical, I want to convince you that the name of the game in this field is to be diverse, is to basically be curious and interested in a whole bunch of different things and find interesting connections which other people, basically can't, because nobody is really studying everything. Most people focus on one thing at a time, so dark matter or black holes or gravitational waves or QCD or statistical mechanics or whatever. Like, you choose something and you specialize in it. This is very important. You have to be specialist at something. But astroparticle physics is one of those fields where, on top of being a specialist at something, if you have broad knowledge over a wide variety of things, you find interesting connections and you can do some, what I hope you will agree, is interesting work. So that's the big picture. That astroparticle physics is an interdisciplinary field. I don't like the word very much because everything is physics. I hope we agree with that. But it's a field where variety of techniques, variety of ideas, variety of tools, variety of observations can be synthesized to do something interesting. So that's what I like about astroparticle physics. That's the excitement that I'll try to convey to you. Okay? Any questions at this point? No? Great. Let's start. Alright. So this is sort of what we believe the night sky looks like if you had powerful telescopes. And what this is a Hubble deep field image in the background, and I've superimposed a Hubble image of a galaxy. Okay, so this is roughly what, let's say, one part of some sky will look like. And one could wonder what's there in the dark, gaps that you see in between the brightly lit spots. Of course, one thing you have to ask is that what are those brightly lit spots? Are those stars? Actually, no. Most of these are galaxies. Okay, so I'm showing one of these galaxies in big, but most of these other things are also galaxies. They're not stars. The stars are inside the galaxies. But nevertheless, what's there in these gaps in between the brightly lit spots? One might think that maybe nothing. The space is mostly emptiness, is what we are told. But we actually have to recognize that just as in this room, most of the stuff that we can see, this table, me, you, all of this, there is more stuff that we can see. In particular, the air in this room. So it's just because we can't see something doesn't mean that it's empty. The same thing is true of the universe. Okay? So this dark stuff in the universe, actually around every bright spot, let's say a galaxy, there is this cloud of what I have colored in blue here, but you can't actually see, is what we believe, is dark matter. So dark matter shouldn't be thought of as in some very mysterious, complicated way. Just in the same way as in chemistry, there was a point of time we knew about iron and carbon and sulfur, but we did not know about oxygen and nitrogen and eventually xenon and argon and whatever else, right? So Lavoisier discovered very famously that air was made of nitrogen, oxygen, whatever. And then it took another 100 years. Eventually we discovered that atmospheric air has a bunch of gases, oxygen, nitrogen, argon and so on. But we discovered the chemical composition of this invisible matter. Right? This happened in chemistry in the late 1700s, early 1800s. 1894 is when argon was figured out. There's a nice story to that. If there's time, I'll tell you at the end of the talk. Okay? So this discovery of invisible ordinary matter is one of the great triumphs of chemistry. There were several Nobel Prizes, Raleigh and Ramsay, they got Nobel Prizes for discovering argon and so on. Now, when it comes to fundamental matter, electrons, protons, neutrinos, neutrons and so on, there's also this problem of invisible fundamental matter. We're not talking about chemistry now, we're talking about all chemistry, all periodic elements are of course made of electrons, protons and neutrons. But now we're saying that there is some invisible fundamental matter which we're not seeing, but that's the stuff that forms this dark matter. Okay? And how do we know this? I'll come to that in a few seconds, but basically this is the picture to have in mind, that galaxies are surrounded by this new kind of dark matter called dark matter, which we can't see, but it's there. The question is, how will we find it? Even more importantly, is not just around any one of these galaxies, but if you look at the universe at the largest scales, this is a simulation by the way. So the previous one was a composite of a Hubble picture and this cartoon simulation of a dark matter halo. This is a full computer simulation and the scale is given here, 100 million light years. And all the yellow dots here are simulations of visible galaxies. And I think you can see this slightly hazy, bluey, fog inside which these galaxies sit. That's the computer simulation of what dark matter should look like on the larger scales of the universe. Okay, 100 million light years. So basically the idea is that there is this matter that's very similar to our ordinary matter, in the sense that it interacts through gravity, and therefore if it's interacting through gravity, it will try to cluster. And if we leave some matter, it wants to come together. But it does not have electromagnetic interactions and these other interactions like weak and strong interactions. And so as a result, this stuff can cluster a bit more than normal matter. Normal matter cannot really cluster too much because once it becomes fairly tight, it heats up and maybe it can form stars. There's some pressure, there's some radiation pressure. So normal matter cannot just collapse very easily. But dark matter can collapse a bit more easily. And what happens in the early universe is that this dark matter starts collapsing and forms regions where there is high density. And you should picture them as gravitational potential wells because the matter density is high, so the gravitational potential becomes very deep. And then all the ordinary matter then falls into this gravitational potential. And then they form galaxies and galaxy clusters and other things. And that's why these dots are exactly where the dark matter density is high. Okay, so that's the picture to keep in mind. Now, this picture is actually something that has been developed over several decades, and now we know that about 70% of the entire energy of our universe is made of something called dark energy. This has got nothing to do with dark matter. This dark energy is not dark matter. You should not think of E equal to mc square. This dark energy is just a different name for the fact that the rate at which the universe is expanding is increasing. So acceleration of the universe. This has got nothing to do with dark matter. So for the rest of the talk we will ignore this 68%. But about 27%, so about a quarter of the entire energy of the universe is this thing called dark matter. And then everything else that we know of is the rest, about 5% or so. So that includes atoms, so hydrogen, helium. There's almost nothing of anything else. There's some neutrinos, and there's like less than 1% of stars. So that's the composition of the universe. And what we're really now faced with is this, okay, there's some evidence which I'll tell you about in the next slide, that there is this thing called dark matter, but we don't know what it is. Okay, so what's the evidence for dark matter? So far what I've told you, is this story that galaxies live in a halo of dark matter. All the structure in the universe is embedded in this fog of dark matter, and this dark matter is some new substance, some new particle, let's say, not an electron, not a proton, not a neutron, none of the particles that we know of. But how do we know this? So let me try and convince you how we know this. So there are many lines of evidence that tell us this, and it would be a separate talk on its own to tell you about the evidence for dark matter. You may have heard about rotation curves and such things, but let me tell you about what I consider is the modern and more robust cosmological evidence for dark matter. So the first is the one that you see on the top left. So the x-axis, the horizontal axis, is inverse of the angle in the sky that you see. Okay, so you take 2 points on the sky and you ask what is the angular, separation between 2 points. And you ask, across these 2 points, if I measure the temperature of the sky, is this temperature in general such that these 2 points are both slightly high or slightly low. Why there is a temperature in the sky, where does this temperature come from? Let me come to that in a second. But basically, this is the cosmic microwave background radiation that you may have heard about. And if you look at the 2-point correlation function, which is what I just described, it is predicted to have this, wiggly pattern that you see there. And the precise shape of this, relation between the temperature at 2 points on the sky depends on the nature of the material that makes up the universe. Why? Because what you are seeing here are nothing but the waves that existed in the early universe plasma. So very long ago, early in the universe was hot, dense, it was a plasma. And so if you disturb this plasma somewhere, what happens is that, now suppose you gather up a bit of material in some place, there's more density, then this highly dense region will attract more material, it will fall in here. When stuff falls in, the density will grow even more. Eventually it will heat up. Once it heats up, there is radiation pressure and it will push things out. So there are two opposing forces. There is gravity that pulls things in and there is radiation pressure that pushes things out. Whenever there are opposing forces, you set up oscillations. Okay? If there are oscillations at each point, this is precisely the situation in which in the fluid you can have waves. Waves can propagate. Now, these various peaks are the wavelengths of these waves, that how far have these waves propagated. And the amplitude and the wavelengths of these waves depend on the nature of this material in which the waves are propagated. Now it turns out that if you have dark matter, which does not have radiation pressure by definition, that will change the slope, among other things, of this tail of this curve. If you have more dark matter, this damping is less. If you have less dark matter, then it damps more quickly. Okay? And so we can measure that slope quite well. All of those are actual data points, and from that we know how much dark matter is there. So this is the cosmic microwave background radiation that tells us about dark matter. Okay? Just how much dark matter is there, we know it from the shape of that curve. You don't have to actually know about the details of this curve, just the shape tells you. Now the second plot that you see is basically the same thing but done using galaxies. So now you basically count galaxies in the sky and you ask basically what is the probability that I have an excess of galaxies at a given angular separation related to some baseline, and that also shows this curve. Actually there are imperceptible small oscillations right after the peak. They're very hard to see, but it's there. It's called the baryon acoustic oscillation in some sense. Now, again, the shape and the features of this curve tell you how much dark matter is there, and we understand that there's 27% of dark matter. So what that tells you is that, okay, we need some new form of matter, or well, I don't know whether I should call it new. We need a form of matter that does not have radiation pressure but has gravity. That's all. But then you could ask that, well, maybe it's neutrons. Neutrons are electrically neutral. They have mass. So good, I'll have gravitational attraction. Maybe that works. Maybe I don't need anything more. The point is, of course, neutrons decay after some time. So you could say that, okay, maybe not neutrons, but maybe something else. Maybe these are just, neutral atoms. Okay? Neutral atoms are fine. But the point is, if neutral atoms, fall in and they become very dense, eventually they will collide and get heated up and they will develop radiation pressure. So neutral atoms are fine as well. So then actually in the particle physics world, there is no other candidate except for one, which is something called neutrinos. So neutrinos are like electrons. If you don't know about them, if you know, then you know what I'm talking about. But in case you've never heard about neutrinos, neutrinos are elementary particles just like electrons, but a million times lighter at least and without electric charge. Okay? So these are neutral electrons which are a million times lighter than electrons. So these are called neutrinos. The three kinds of them. Now, you could say that, well, maybe this neutral particle could be dark matter then, and this is something that was considered very seriously up until the 1980s. But it turns out that when you have such a light particle, it moves very fast. And if it moves very fast, then you cannot keep it concentrated in small regions. So you can't have a density bump which is very sharp. It will get smeared out. If small scale density bumps get smeared out, then you cannot have excess, probability for a pair at those small densities, right? Because everything is at larger angular separations. And so what that would have done is that this curve that you see, it would have kind of cut off a bit earlier. But the fact that it does not, that tells you that neutrinos cannot be done. Okay? So this is how we know that there is something called dark matter, and this dark matter cannot be any of the particles that we know. This third picture that you see is another extraordinarily important thing. This came up in 2006. It's called the bullet cluster. Let me take another minute to explain this plot to you. So what you are seeing here is a composite of three different things. So first let's pay attention to the blue stuff. So the blue stuff is a map of the total mass of the system that has been derived by just looking at how light bends around it. So there are like stars in the background, and because of gravitational lensing, the light bends, and you can use that to figure out where is most of the mass. And you find that that's in that blue block region. Okay? The second picture that is in that composite is an X-ray image of where is most of the gas. Because that's measuring hot gas, and that's basically in that pink region. And the third picture is in yellow. It is a picture of where all the stars or galaxies in the background are. And so what's happened here is that two clusters of galaxies, so these are blobs, each blob with about 1,000 galaxies in them, they have collided, and actually the galaxies themselves don't collide, they just pass, because it's like a lot of empty space in between, and the galaxies actually don't collide head on, they just pass through each other like ghosts. And so does most of the dark matter, because the dark matter doesn't interact enough. But the neutral gas that was there in these regions, that smashes into each other and gets heated up, and it forms these shock heated gases. In fact, you see that sharp bow shock that you see when you have supersonic shock waves in hot gases. So that's what has happened here. Now what that tells us is that you see that dark matter, because it did not, matter would have also done what the gas did. Okay, so that's how we know that this dark matter is weakly interacting, like it doesn't interact like normal matter. It does gravitate, which is why it forms all these structures. So what that tells us is that there is this new form of matter that gravitates but does not have radiation pressure, and it cannot be any particle that we know. It's some new particle. We'll have to discover a new particle here. But that's where we stand. We don't know how to proceed. Okay, so one naive, but maybe not so naive question to ask would be that why couldn't it just be some boring thing like maybe a bunch of planets, So maybe ordinary matter has like coalesced into things like very, dark objects like planets, which are not hot, and they would also not collide. They would just pass by each other because they're so small that they don't find each other in a big cloud, right? Or maybe black holes for all you care. The answer is that? Alright. Okay, so you might worry that why am I insisting that it has to be something new? Why couldn't it just be ordinary matter packaged into some very, cold, dense, boring astrophysical object, some, star, or not star, but some dark light star. So the answer is that whatever it must have been early enough in the universe, when everything was melted down into some plasma, if this was not a truly new thing, if it was just made of normal electrons, protons and neutrons, it would screw up how much of deuterium and lithium and other things were made, because the rate at which various nuclear elements are made depends very sensitively on basically how many electrons and how many neutrinos and how many protons and neutrons you have. Okay, so we know exactly what that abundance is, and that's not consistent with having too many extra, let's say, protons or neutrons or electrons or whatever. So there's one exception, of course, and that's the first, let's say, of the three results that I'll talk about. So we'll come to feeding. So, but let me start by first telling you a little bit about this thing called primordial black holes. So this is an exotic kind of black holes. It was first, I think, proposed by Russian physicist Zeldovich and Novikov, and independently, I believe, or at least very soon, by Stephen Hawking, and then worked on by many others. And the idea is this, that very early in the universe, before anything has happened, before stars have formed, before galaxies have formed, before anything else has happened, very early in the universe, there's like matter everywhere at some density. But if in some region that density is a bit too high, then that region can just collapse by gravitational collapse into a black hole. This kind of a black hole is called a primordial black hole. This is a black hole that is not made through the evolution of a star. Usually black holes are made when there's a star, it runs out of its fusion fuel, so the radiation pressure is lost, and then it collapses, makes a black hole. And then there's this Chandrasekhar limit and so on. But suppose you could just collapse some density fluctuation that is not subject to any Chandrasekhar limit or anything. So you can just form black holes of any mass. And in fact, what will typically happen is that you would collapse the region that is causally connected, which is to say that the entire region over which basically light can propagate in what is called a Hubble time, that whole region can collapse into a black hole. And so the mass of a primordial black hole that is created at any given time depends basically on the volume in the region that is causally connected. So at any given point of time, there is only so much part of the universe from which I could have gained information, right? So that entire region is what I would call the causally connected region, and so that entire region collapses into a black hole. So early in the universe, these regions are small, and so the masses of these black holes are also small. But of course, they can also be big, so we don't know exactly what these masses are. So there's a wide range of masses. So this red scale here goes all the way from 10 to the minus 17 times the mass of the sun to 10 to the 5 times the mass of the sun. We don't know, and so all of these are acceptable masses for these primordial black holes. So there are other ways of making primordial black holes, but I'm not going there. Now, question is, how do you look for these primordial black holes, and can these primordial black holes be actually some part of the dark matter? Oops. Yeah. Okay. So I've told you that there can be these density fluctuations in the early universe which collapse and make black holes. If I can make these black holes, they would not be subject to the kind of arguments that I just made before, right? They would not have screwed up my formation of nuclear elements. They would basically behave identically as far as this cosmic microwave background, or this how the galaxies are distributed, or this bullet cluster. All of this would work out just fine. There would be no problem. So why can't primordial black holes be dark matter? So that's the question. And people have worried about this question, and we believe that primordial black holes cannot make up all of the dark matter that we have in the universe, except in a very small range. So again, here on the horizontal axis is the mass of the primordial black hole, and on the vertical axis the fraction of the total dark matter that could be in the form of primordial black holes. Okay? So on the top is 10 to the 0, that's like all of the dark matter is primordial black holes. And here 10 power minus 4 is like 1 out of 10,000 of the total dark matter is primordial black holes. Now at the very high mass end, there are constraints from the fact that if you have these primordial black holes, they will accrete gas onto them. This gas will get heated up and we'll be able to see that. For example, as foreground distortions on the CMB. So that's this Planck constraint. Then of course, if there are these primordial black holes, they could be merging. And then they would contribute to the rate at which LIGO is seeing mergers of black holes. That puts a constraint also. Similarly, if there are black holes in the sky, they would start lensing light of stars that are behind them. And you would suddenly start seeing this excess amount of, bending of light, which you don't. All of these can be used to put constraints which are in these shaded regions. So in the shaded region, basically you say that you can't have that much of dark matter at that mass of PBH. Right? So basically you say that if you are at mass of the black hole, primordial black hole being 10 to the 25 grams, then you can't have more than about 1% of the total dark matter in the form of primordial black holes of that mass. Okay, so the shaded regions are what we would call rule out. So you'll see many of these exclusion plots. So much of astroparticle physics, until you discover something, is about slowly ruling out what is impossible. It's a very Sherlockian principle. Okay, now the stuff to the left, this colored stuff, I'll tell you a bit more about in a second. But this gap in between, the region where you don't see any shaded regions, is roughly the mass of an asteroid. Slightly less than the moon. And at that mass, all of the dark matter could be made of primordial black holes. We don't know. Okay? But we know that they cannot be a bit smaller than that. And how do we know that? This is the first punchline in some sense. So the idea is that black holes have a temperature. For any black hole of a given mass m, it has a temperature that goes as 1 over m. Okay? And the smaller the mass of the black hole, the higher this temperature. Once you make the black hole mass too small, the temperature is high enough, that this temperature is larger than the mass of some of the elementary particles like electrons, let's say, or neutrinos. Photons are of course massless, but photons have energy E. And if let's say the temperature T is such that kBT is larger than some energy E, then photons of that energy can be produced quite easily from those black holes. But easily meaning how? Through Hawking radiation. Okay? So Hawking radiation is like this. This is a black hole, and over a very long time, Hawking radiation is an incredibly slow process. But nevertheless, this black hole radiates its energy or its mass in terms of photons, but also these particles, if the temperature is high enough. Okay? What we guessed is that for these very low mass black holes that I just showed you here, the temperature is large enough that we said that, well, other than making photons, which people had already considered, they should also be making neutrinos, which are also these light particles. And so we computed how many neutrinos should be produced. And we have neutrino telescopes, so we can then look for those neutrinos, which we don't find. And then we say that, well, if dark matter had a large component of these light primordial black holes, we would have already seen these extra neutrinos from wherever dark matter is. We don't, and therefore we conclude that a certain fraction of dark matter in the form of primordial black holes is not allowed. So that's this. So on the x-axis is the mass of this primordial black hole. On the y-axis is the fraction of dark matter in the form of these primordial black holes. The regions in red are ruled out. The different lines actually correspond to how fast these primordial black holes are spinning. Because it depends a bit on whether the black holes spin or not. But that doesn't matter. As you can see, that uncertainty is small. Basically about 1% of all the dark matter in the form of primordial black holes is strongly constrained by neutrino observations. So this is my first illustration of how there is a confluence of techniques. There's neutrino physics on one side and black holes, and then there's dark matter, and somehow all of these things come together into one concrete statement. Of course, this limit turns out to be much bigger other limits, from normal electromagnetic telescope, you're looking for photons, for example. So all these different lines correspond to these different constraints, but basically the same idea, that there is a primordial black hole, it's radiating either photons or electrons or neutrinos, and you try to look for this radiation, you don't find it, and therefore you set a bound. You set a constraint on how much of the dark matter is in the form of this primordial black holes of this mass, and these are all these constraints. One of the reasons why I'm showing you this plot is if you at some point of time you take the effort to read who these results are by, you will find that more than 50% of the results actually come from people in our country. So this is one of the areas, like very small niche areas, but nevertheless one of these niche areas in physics, astroparticle physics, where where the work done in our country has been outsized and significantly important. So it should make us happy. Okay. So far I've told you about how primordial black holes can be a fraction of the dark matter and how that can be limited by looking for fading of these light primordial black holes. Okay. Now I want to switch gears. Now I want to get away from this idea that dark matter is made of something ordinary, in the sense it just collapsed mass. Now we will move into this territory that no, we need some new particle. Dark matter isn't just made of black holes, but dark matter is some new particle which coalesces and forms structures and all of that, but we don't know what it is and we would like to know what it is. Now here is where things become very hard, because we don't know what is the nature of this new particle, so we'll have to make guesses and then we'll have to verify those guesses. Okay, that's the way this game will be played. So here you might be familiar with some of this. So the idea is that as a theorist, you just write down a bunch of ideas about what can be dark matter. You write dark matter and then you write some people axions, and axions are something that could be dark matter, and so on. So let me tell you about two ideas about what dark matter could be. There are actually hundreds, but let's just go into two of them. I'll go over the first one very quickly. Don't bother if you don't catch everything, because the whole purpose of this first thing is to set up contrast with the next thing. And that the next thing is what's more important. So there's something called annihilating particle dark matter. The idea is that these particles is only one kind. So normally we are used to particles having antiparticles. In the case of this kind of dark matter, there is no antiparticle. The particle is its own antiparticle. And these particles shown here in red, they just meet and annihilate into normal particles. Let's say electron positron, electron anti-electron. So just shown in blue. And this is of course happening in the early universe. As the temperature falls below the mass of the dark matter particle, the red blobs, the dark matter blobs, can combine to make the blue blobs, which are the standard model particles, which are light. But the blue blobs cannot back convert into the red blobs because there isn't enough energy. Okay? So suddenly you start reducing the amount of dark matter in the universe. Now the temperature keeps falling in the universe is expanding, and dark matter and all ordinary matter is becoming dilute. Eventually you reach a point where in a volume of the radius of one mean free path of the dark matter particle, I'm guessing all of you know about mean free paths, right? So in one mean free path sphere of dark matter, if you have only one dark matter particle left on average, then this dark matter particle cannot anymore annihilate into anything else, and you will be left with this amount of dark matter. This is called chemical freeze out of dark matter. You can compute this using a bunch of differential equations, but basically this is what's going on. Okay? This is called a WIMP freeze out. There are all sorts of names for it. But this happens when dark matter is made of a particle that can annihilate with itself. Yes?
This access going to standard model particles. So
yeah.
What is the mediating?
Yeah, so we don't know. So this is an assumption. We don't really know. The question is that how do we know how much of this dark matter particle is going into standard model particles and what mediates this interaction and so on? We don't. So we make some assumption.
It assumes that there will be some higher wave group where things would be completely.
Yeah. So there is some model dependent thing. So there are 100 different assumptions one can make. we are not going to make any assumptions. We are trying to be as general as possible. The idea is that whatever be it, this is a generic phenomenology that is expected to occur. And if this occurs, you expect that this kind of dark matter annihilation is ongoing even now in regions where dark matter is dense, for example in the center of galaxies. So that's a galaxy, that's Earth, we are sitting and looking at some other galaxy, and the two dark matter particles here can annihilate and produce, let's say, some primordial particles at the same rate at which that whole annihilation in the early universe would have happened, which produced this dark matter in the first place. Now, there is some rate. The rate at which this interaction occurs is given by the density, cross-section, relative velocities and so on. So the fact that you don't see such dark matter interactions, because you don't see these electrons that I am claiming should be there, you can then put bounds. And instead of electrons, you could have some other particles, for example, charged particles, protons, antiprotons, or whatever, photons. So you could use any kind of messenger, any kind of instrument. You could look at the dark matter in a bunch of different sources, but now I have given you whatever n times m times k different research problems. Now you choose a source, a messenger, and a detector, and you can calculate a signal for what should be the annihilation rate for some dark matter model. You can write millions of dark matter papers. People have done that. You are too late. Joke. Anyway, so this is what is called indirect dark matter detection. You search for dark matter annihilation in astrophysical objects. The sad story is that people have tried this, nothing has been seen so far, and again on the x-axis the different experiments. On the x-axis dark matter mass, on the y-axis something like the rate at which the dark matter is annihilating, and again these lines, everything above that is ruled out. So you basically know that dark matter is not annihilating at a given rate, it has to be weaker than that. So there is strong bounds. Interestingly, you may be able to see that in almost all of these plots there is a horizontal-ish line that's drawn, right? That's not a bound, that's the rate that is predicted by the fact that we know how much dark matter is there today. And this wind freeze out that I told you about 2 slides back, that predicts that you need that cross section, that rate, in order to reproduce the currently seen amount of dark matter. So when your experimental shaded regions go below the horizontal line, that's when basically you have started ruling out interesting models. Okay, and that's already happened over the last 10 years. Okay, so that's the current state of the art. This is one of the examples where you see this dashed line, and these shaded regions are now beginning to go below that. In fact, they've gone far below. These plots are from 10 years ago. Okay, so now the contrast. So I told you about dark matter that annihilates with itself. But see, this is not the normal form of matter. Electrons don't annihilate with electrons. Electrons need anti-electrons to annihilate with, right? So why are we coming up with some bizarre idea about dark matter? Maybe dark matter is much more like our ordinary matter, like electrons, which need some antiparticle. And what has happened is in the early universe there was both dark matter and anti-dark matter, and it annihilated, and there was a little bit of excess of the dark matter which is left behind, and the rest has gone into some photons or whatever else, which we don't care about. So what we are seeing today is just this one kind of dark matter that does not annihilate with itself. This is called asymmetric dark matter. Okay? And this is also a popular theory. For either asymmetric or symmetric dark matter, the one that I told you before, there is this expectation that this dark matter can interact with, let's say, normal ordinary particles. It can come and hit, let's say, one of your particles, and then it will recoil. Just billiard ball collisions. So the dark matter particle comes in, you have an electron sitting here, it interacts, so the electron goes away, and the dark matter goes in some other direction. You're just conserving energy and momentum. You learn to calculate this. Okay, so we can compute the rate at which these things happen. Again, some in sigma with some rate. And then you ask, again, the same game, that there is dark matter all around us. Some of this dark matter is coming and hitting my atoms inside my detector. I ask, how many such collisions do I expect? If I don't see any collisions, then I know that my rate estimate was larger than what is being seen. and what that does, it puts a limit on the cross-section signal, the rate at which the interaction happens. Again, this has been done for several decades, and as a function of mass and the rate of interactions, you again put these constraints. The shaded regions are models. These blobs at the bottom, these are models of dark matter that are being ruled out. Now this is already from 15 years ago. I used to think of this as the state of the art when I started giving some of these dark matter talks. This is the state today. Actually, from the earliest times, these limits have improved by something like 10 to 12 orders of magnitude. So they used to be at 10 power minus 36, 37 early on, and now we are at 10 power minus 48 in some cases. So like 12 orders of magnitude. So this is no mean feat. To improve upon experiments that they are 10 to the 12 times better than they used to be. This is, I think there are hardly any other fields where such improvements have been made. And yet, we have been very unlucky, we have not found that. One problem is that there is a limit to how much you can go, because you can see there is a blue shaded region underneath. This is the point at which the neutrinos, largely from the sun, the sun produces neutrinos. The neutrinos from the sun start bumping atoms in your experiments and mimicking dark matter interaction. So at some point of time, the rate at which dark matter interacts with your detector starts being smaller or comparable to the rate at which other stuff interacts with your detector, like neutrinos. And then it becomes very hard that even if you see a signal, how will you know whether it came from neutrinos or dark matter? And so this is believed to be a huge problem. This is called the neutrino fog or the neutrino floor. Nobody has a very good idea of how to solve this problem. Okay? So I'll tell you about one of our ideas. This is the second sort of stream, and the last one is very quick, so we'll finish on time. Now comes this whole excitement about LIGO and gravitational waves. So on the left hand side, you must have seen these plots 100 times, right? So LIGO sees mergers of black holes. The Event Horizon Telescope has found evidence of these large, supermassive black holes at the centers of galaxies. That's the right one. You see the, what's called the shadow of the black hole. And so basically, this excitement in these areas have asked a lot of other people working in other areas to wonder, okay, we know that there are all these black holes around us, they're merging, and we can even, detect the gravitational waves from some of these black holes. We can also image some of these large black holes at the centers of galaxies. We know where they are, what their masses are. Can we now start using these as tools to learn more about dark matter? Okay, this would not have been possible more than 10 years ago. Okay, but because there's this new thing that has happened since 2015 or so, people who work in dark matter can ask this question that, okay, fine, you guys are excited about black holes and gravitational waves. How about I start using this as a dark matter detection device? Okay, so that's what the next two things are about. Okay, so let me skip a little bit of this, but yeah, let me just skip this slide. So this is the second punchline, that what can happen is that if there is dark matter of this non-annihilating kind, okay, that's shown in this red halo, they can get attracted to neutron stars and get lodged inside the neutron stars, by just scattering with the neutrons. And eventually you attract enough of this dark matter. This dark matter, of course, does not have any radiation pressure, so it just keeps accumulating. And at some point of time, you have enough dark matter that this whole thing can just collapse to a black hole in the middle of a neutron star that is still alive. Okay. Now, one thing you may ask, if some of you know about the Chandrasekhar limit, is that this collapse to a black hole occurs at a particular mass and above. You need to have at least 1.4 solar masses before ordinary matter collapses to black holes. So, will I need to acquire 1.4 solar masses worth of dark matter in order to undergo this collapse? The answer is no. Because this limit actually goes as 1 over the mass square, or 1 over the mass cube in some other cases, depends on whether it's a boson or a fermion. The limit can be much lower if the dark matter is heavier than ordinary matter. So instead of protons, which are let's say 1 GeV, if dark matter is let's say 1000 times or 10,000 times heavier than the proton, so a heavy particle, then the Chandrasekhar mass limit can be brought down by like 8 orders of magnitude. So it's insignificant, like 10 power minus 8 solar masses is nothing. So just by accreting a tiny amount of dark matter, the neutron star can develop a small black hole at its center. Then this tiny black hole, the micro black hole, starts eating up the neutron star from inside, and the entire neutron star becomes a black hole. Now the magic here is that the neutron star can let's say have a mass of 1 solar mass. Okay, and it accreted a tiny amount of dark matter, 10 power minus 8 solar masses. So the total mass is still 1 solar mass, right? Plus 10 power minus 8, so 8 decimal places. And this whole thing has gone into a black hole. So the final mass of the black hole is like 1 solar mass, which you can just never produce. Like, Chandrasekhar limit is 1.4. So typically you don't produce black holes that are actually smaller than 2.7, 2.8 solar masses. That's what is called the Tolman-Oppenheimer-Volkoff limit. Basically tells you instead of normal matter, nuclear matter needs to collapse, what is the minimum mass that you need. So about 3 solar masses. So you can make black holes which are significantly lighter than you would have gotten out of stars. Okay, so these are exotic black holes. We call them transmuted black holes. This will happen if you have heavy non-annihilating dark matter. Okay, so if your dark matter is a heavy non-annihilating particle, then it can accumulate in neutron stars and make this micro black hole, which then eventually makes transmuted black holes. Yes.
What is the need for neutron stars? Why can't dark matter just collapse like normal matter in the universe?
Good. The question is, why do I need the original neutron star in the first place? It's a very good question. See, dark matter is distributed fairly uniformly, okay, and it has some angular, so it doesn't really just collapse on itself. It's slightly subtle argument because I just told you that dark matter likes to collapse. So I have to walk back from that a little bit because it isn't quite that simple. Nevertheless, why the neutron star is useful is that the neutron star is heavy and compact and very small. So it produces a very deep potential there. So dark matter is attracted to it. As it is attracted, it also speeds up. But once it enters the neutron star, it can undergo a lot of collisions because the neutron star is dense. And then its velocity can fall below its escape velocity for the neutron star and it gets trapped. So that's how it works. So that's the reason why it mostly works for neutron stars and white dwarfs. It doesn't quite work as well for ordinary stars like main sequence stars. So, basically simplifying a whole bunch of things here, but I hope I've answered your question. Is there another one? Yeah.
So just I was wondering that what about the distribution of neutrons?
Okay.
Does it actually keep track of?
So, does the evolution of the neutron star get affected by the fact that dark matter is being accreted? Basically not at this level. So the amount of dark matter being accreted is 10 power minus 8 solar masses or so. This is incredibly small. So this basically doesn't do very much. Okay, except that eventually once you form that black hole, it just makes the entire neutron star collapse.
So that will be missing now. That's the neutron.
Correct. So that is the idea. So that is the idea, indeed. So
that's my exact question. That you see that kind of
good
disappearance of neutron star.
Give me 30 seconds. So I'm coming exactly there. Anyway, so this is the idea. Now it turns out that for choices of dark matter mass and cross section that are not already ruled out, so that grey triangle shaped region at the top left is the bound from these experiments that I just told you about. Okay, and this pink region is where this transition can happen. Now there are also other things on this plot, but I'm not telling you about them, ask me later. But in the pink region it is allowed. So clearly it is allowed. Okay, and can we go and look for them? And how will we look for them? And so that's exactly Professor Lack's question. How would we find these fantastic beasts? And the idea is that they will have to happen in regions where there is a lot of background dark matter density. Typically you need compact stars like neutron stars, will not happen for main sequence stars very easily. And they can merge with another compact object and make gravitational waves. So we can look for them. So there are a bunch of other things that we skip. let me just skip this as well, and this is the result. As a function of the dark matter mass and this interaction strength, again on the top left, this triangular region is the bound that comes from dark matter direct detection experiments, and the diagonal regions that are going like this. So let me focus first on the pink region on the top right. That's the bound that comes from the fact that if you have these exotic black holes, they would be merging, and LIGO does not see such exotic black holes, and that's where this bound comes from. Okay, LIGO over the next decade will improve its sensitivity and can give a bound that's as strong as this dashed region, you know, that you see, LIGO forecast, and that's, you know, again many orders of magnitude better than what we have currently. And most importantly, you will see that there is this other diagonal line called neutrino flow, and you see these limits are going well below that neutrino flow, which, you know, for the low mass end we don't know how to go below that, but here it doesn't matter. Here we know how to go. So you can go below the neutrino flow and look for dark matter. And let me skip over a bunch of things here. I overestimated how much I will have to explain. So the idea is that you can try to ask whether what you're seeing is a neutron star or a black hole of this exotic black hole, and we have ways of telling black holes and neutron stars apart. So let me skip that. Okay, now my final thing. I think I should finish in 5 minutes. Okay. So I told you that if dark matter is this heavy non-annihilating particle, then it has the ability to form a tiny black hole at the center of neutron stars, convert the neutron star to a black hole, and then we can look for such low mass black holes. Okay, and the fact that we don't find these exotic black holes allows us to then tell something about dark matter, this heavy non-annihilating dark matter. Now, I want to do something much more general. I'm not going to assume anything about the nature of dark matter. I'm not going to assume that it's a heavy non-annihilating dark matter. I'm going to assume that whatever this dark matter is, some new particle, and it just clusters. Now, the only thing I will assume is that it is not something that is so light, you know, the mass is so small that it has a de Broglie wavelength that is very large. Okay, so it's not a wave, it's a particle. Now that's the only thing that I will now assume. Given that there is a lot of work that tells us that if you have dark matter, it clusters, it makes these blobs called halos, and the centers of these blobs, if you put a black hole in there, a big black hole like there's one at the center of our galaxy, then the dark matter piles up near the center and forms a spike. Okay? These dark, by the way, this is pure classical mechanics. You know, basically there is a black hole at the center and there's dark matter halo around it. As the black hole eats up more of the dark matter, the black hole mass grows. So this is like a classical mechanics problem where you have a bunch of particles in a gravitational potential that is increasing with time. You know, that is like becoming deeper with time. This is called adiabatic, you know, invariance. You know, if you've done classical mechanics at a slightly higher level, you know how to compute these things, and from that you can compute that that the shape of this spike near you know, the center is a power law that goes as 1 divided by r to the power 7 by 3. Okay, so you can compute this. It's not something that comes out of computers, it comes out of a real calculation. Okay, so that's the 7/3 index. So the halo has a 7/3 spike. This, you know, was calculated long ago by Londo and said. Question is, can you look for it? Why do you want to look for it? Because this would be kind of a model independent general way to look for all kinds of particle dark matter. Any particle that accumulates in this way, you know, it's supposed to give you the 7/3. You can be away from 7/3 for astrophysical reasons. We'll not go into that. So what we thought about is this idea. Complicated looking slide, but bear with me. So what you are seeing here, that grey blob is the dark matter halo. Okay, it's a spherical dark matter. And the density at the center of this halo is increasing as some 1 over r to the power 7 by 3, let's say. and because there is some big black hole. The big black hole is actually not important except it is needed to get this spike. Now imagine I want to measure that I have this 7/3 profile. How will I do that? One way would have been that if you just take a star and let it fall in the gravitational potential of this spike, and you measure the Doppler shift of this star, that Doppler shift would be time dependent because it's falling, so it's accelerating. So if you know r as a function of t, you can compute all its derivatives. So you know the acceleration, the rate of change of acceleration, and so on and so on and so on. And if you could measure those, you would be able to reconstruct the profile because the potential is in some way related to the trajectory at a point particle. So if you could do that arbitrarily precisely with a star, that's what you would do. But the problem is that these accelerations are very small and you can't measure these Doppler shifts very easily with a star. So the idea here is that instead of a star, make a binary merging black hole fall into the air. Now this is an oscillatory signal. You know, the merging black hole is a oscillatory signal with a frequency. And this base frequency object is falling into a potential which is modifying or modulating an oscillatory signal. So everyone who has done any kind of signal processing knows that this is a much better situation where a known frequency is being modulated by a slow long-term effect. This is much easier to extract because you can basically just do what is known as a lock-in amplifier technique, or in other words, do a Fourier transform. So do a Fourier transform, you can pick out this. So that's what you can do with a binary black hole merger that's happening in this spiky region. So falling binary, so this is the third part, the falling binary tracks the gravitational potential and you just do all the calculations that are needed. It turns out basically that the gravitational wave signal, which is written here, for this falling binary is given by the static binary multiplied by this e to the power I times some e to the power I phase. This phase can then be computed. And it depends on the potential, the spiky nature of it. So you then simply just fit for the shape of the potential, and what one can show is that the 7/3 corresponds to something like 2.33. Okay, and what these curves, shaded curves are telling you is that how well can you reconstruct the 7/3 given realistic situation. And you can see that you can reconstruct it to about 5 to 10%. So you can say that this spike is 7/3 up to 5 to 10% precision. That's incredibly accurate. There's no other known method that can do this at this scale. And if you could do this would be a way of not just knowing that there are supermassive black holes at the center of galaxies, but also experimentally, observationally establishing that they have created these dark matter spikes around them. Okay? And not only that, also measuring those things. So then, because we know the shape of this thing, this will also tell us something about, for example, what is the free streaming length of dark matter. That dark matter de Broglie wavelength cannot be larger than that. We should put more interesting constraints on dark matter. So with that, I think I'll stop. I've told you about 3 different ways of engaging with dark matter using current, let's say, excitement in black holes and gravitational waves. I hope I have conveyed to you this excitement and kind of nimble-footedness that is needed to make contact with a variety of different ideas like neutrino physics and astrophysics and in some cases nuclear physics and gravitational physics and saying something new about dark matter using current developments in all sorts of different areas. And I've been very lucky to have worked with a bunch of students and postdocs, fellow faculty members mostly on the right here. Very famously, you don't see your Professor Bhavesh on this list because Bhavesh and I did far more difficult and hands-on stuff.
we work on effectively nuclear neutrino physics, not as exotic stuff as this, but anyway, these are the people who have been involved in the work that I spoke to today about. And with that, I'll stop and I'll take any more questions if there are any. Thank you very much.
Last slide where you showed the pictures of all the collaborators. Kumar is the one who did it from the CTS. Our student. So it's a decision.
I guess, yeah, this definitely
2013.
I didn't know that.
PhD from ICTP.
Aditya was a PhD student in the US, I think, if I'm not probably mistaken. But he was a postdoc at ICTP. Oh, you mean Aditya? I'm so sorry. I'm talking about Shashwat, who's also. Aditya Vijay is from Whitfield. You are 100%.
Yeah.
Yes. Aditya is
2013.
Yes. You're absolutely right. I was thinking of.
ICTP.
Okay.
I have a couple of questions. I'll ask one. So this thing that you said about this the last one, where you were showing this plot, there's a binary which is moving under that. So there is a phase modulation because of the spike, right? But there will be another phase modulation because of that phase mass. So that will give the third body sort of again. That will also modulate.
Yeah.
That's right. So how do you guys put it?
Very nice. So, okay, this is a very good question. Also, not too technical. I have the slide to be able to explain this. So the question is that I told you that this binary is falling in the gravitational potential of the star. And there is also the big black hole, which also gives the gravitational potential, which is 1 over r. How do I disentangle these two effects? Okay, that's the question. Now the magic is in looking at these two expressions. One for what is the phase, and the phase basically depends on a bunch of things. Times is gamma sub n. This n measures the different order of derivatives of the line of sight velocity, which is on the next slide. Okay. Now if you see that in the change in phase, in this delta psi, the frequency dependence of this phase shift, which is given in this nu to the n plus 1, u to the minus 8 n minus 5, this actually depends on which order n is there. Okay. Now 1 over r potential will have different derivatives dn dt compared to a different potential that is given by r to the power minus 7 over 3. Given the fact that we can measure not just the acceleration but the acceleration jerk and snap in this particular case, so 3 derivatives, by looking at the frequency dependence of each of these things, you can basically disentangle the different parts of the potential. So in this particular case, we can reject a purely Keplerian potential because of that, and the central black hole would be a pure Keplerian. Okay, so this is how we disentangle until you know about it.
Because this source is interesting in the sense that the binary will emit in the Hertz range and that will emit in the microhertz range, right?
Yes.
So if you look into that microhertz,
That's another way of doing it, except that the gravitational wave emission, because this R, separation between the big black hole and the binary is fairly large. So that gravitational wave loss is super small. So the binary is not merging with the central black hole. So you basically don't see the gravitational waves from that. What you see is the decreasing of the small tight binary, which is far away from the center. Okay, and you measure the slope independent of the mass of the black hole at the center, because you are sensitive to the different derivatives of the potential through the different frequency differences. So it breaks the degeneracy. That's that. Okay.
It said that the dark matter is fairly uniform. So why does it need like a star or a black hole to actually collapse and then for us to detect something over there? Rather than it along with itself, if it's already massive, then why don't we see in an independent black hole or something like that from the
great question. I think it goes back to one of the doubts that was asked in the middle of the talk. That dark matter, I told you, has very little interaction with gravity. Gravity is purely attractive. So anytime you have even a little bit of an over density of dark matter, everything should just collapse there and form black hole. You know, if that's really true, why doesn't that happen? The first order answer here is angular momentum. That stuff that wants to fall in has some angular momentum. This angular momentum cannot be lost. So stuff, instead of falling in, just spins around. Okay? So that's the reason why dark matter doesn't just always fall in. Now, when this is happening in, let's say, neutron star, where I am assuming that the dark matter can interact with the constituents of the neutron star, then once the dark matter comes here, it goes inside the neutron star. Even if it has some angular momentum and tries to spin around, it undergoes lots of collisions, it dissipates the energy, and then can in the end collapse. This would not happen without this background neutron star killing all the angular momentum.
The other question regarding the 2-point correlation function that you shown in the very early parts. Is it suppose if in a direction if you're seeing if you're measuring a line or something, then suppose if we get a particular galaxy that is very faint, we cannot see that. Does it count for that also in that direction?
This is fairly technical. So if you want to talk about the middle plot, which is the galaxy plot, what they do is they first select for a class of galaxies. In this particular case, it's mostly luminous red galaxies, this LRGs or whatever. And then so you have first you select that what is the, let's say, kind of galaxy that you're looking at. They have a particular brightness and size and mass and so on. So you're making sure that things that you're counting are all of the same kind. And now it just simply becomes a question of counting. That now you basically don't care too much about the fact that what is the mass or what is its brightness. Every galaxy now simply counts as a point, and you simply ask that is there a galaxy? Isn't there a galaxy? On a pair that is separated by theta, and then this just becomes a statistics. So that's how this is usually done.
I had to down the first
one, the CMB one.
Suppose if we are measuring the CMB axis,
Yes.
So we are measuring in one direction. Suppose if there is a galaxy, but we are not able to see it.
So I have to, maybe I did not explain this well enough. The CMB is not coming from galaxies. The CMB is coming from the temperature of the plasma in the universe, which is farther. So in the CMB, what you have to do is you have to cut out all the galaxies in front. This is called Bourgeois subtraction. So these are all steps that you have to do to clean your data before you start doing analysis.
What if the galaxy is so far that you cannot
So these are interesting questions. You can never ensure, basically you can never convince me that there isn't an arbitrarily faint galaxy somewhere. But typically so far away you will not be dominated by a galaxy, but rather by a cluster of galaxies. Now clusters of galaxies, they emit in X-rays, and so you use X-ray data to clean the foreground of the CMB data and so on. So there are ways of doing this.
So you were talking about primordial black holes as being a possible candidate for this dark matter in our current framework, and we've not completely eliminated it. So the experiments we were discussing later on of the neutron star absorbing some dark matter and becoming a black hole, and of that falling into a bigger black hole, can those have the same hypothesis with this assumption that dark matter is just primordial black hole?
Nice. Very nice. If you had asked this question about 8 years ago, you could have written a very nice paper. So yes, this is something that people have considered. Initially, there are even some bounds on primordial black holes here, from just exactly that argument, the fact that we don't see neutron stars just exploding. Turns out that if you have primordial black holes, let's say even passing through these neutron stars, first of all, it doesn't happen enough because primordial black holes are small, neutron stars are small, they don't meet. The cross section is too small. Even if it did meet, essentially what happens is the primordial black hole just passes through. It's like a bullet, it just passes through. It's too tight. It's not like the case where gas gets shocked, it goes through each other. So yes, this is an idea that we will consider. No, it doesn't make a big difference.
In the evidences for the dark matter we have, those are the only concrete sort of clues we have of how or what it might be endless, right? So, and then we have several models and hypotheses on how it might work, and then we are testing them and seeing if there is any probability of it happening. Now, we know roughly like 80, whatever the percentage of dark matter West emergency means, that there is this much. So, the hypotheses of several models, if they are not contradicting each other, then it could be a possibility that they contribute some part to it, and then multiple models could work out.
Absolutely.
And one thing I want to ask is that in the bullet crystal sort of thing, when we had discussed that it passes through and then it doesn't interact. Like that was the proof that it doesn't interact, right?
Much, yes.
So one thing I wanted to ask is that we don't know what the nature of dark matter is. And from when we say that it doesn't interact, it means that it doesn't give us any sort of reading to the things that we can observe on our instruments right now, the particles that we know of. So it could be possible that they do have some sort of interaction, but the interaction gives off something totally different.
So let me answer both of your questions. Your first question was, could dark matter be made of multiple things contributing partly? Of course, this is precisely the reason why in this plot I am showing you constraints on what fraction of the dark matter could be made of primordial black holes. So it has to be smaller than, and the rest is something else, which I am not talking about. So I could do this for all kinds of dark matter models. In fact, we should. All dark matter results should be presented as, let's say, limit on what fraction of the dark matter can be in the form of that dark matter. So that's the answer to the first question. The second question that you have is in the bullet cluster. I said that what this picture is showing is that the dark matter has gone past each other and hasn't interacted much. And you say that, well, maybe I'm saying that because I haven't seen any radiation come out. That is one way in which I have arrived at this conclusion. But there is one much easier way in which I am arriving at this conclusion. The fact that this blue stuff has passed through and not slowed down. If this dark matter interacted, then it would just get jumbled up and all stay in the middle. But you see, these two dark matter blobs have gone past. Right? They have gone through each other. They would have been dragged down if they were interacting. So this is the reason why even model independently we know that dark matter has very big interaction. Now I must say that does not mean that dark matter has no interaction other than gravity. Of course we know that dark matter has gravity, but beyond gravity, can I say that dark matter has no interaction? Absolutely not. I can only put an upper limit on its mean free mass. So there is a certain rate at which they would have collected, and I can put say that the collision rate is smaller than so and so. That's the best I can do, and that's what it's been done. And the game is to try and improve our sensitivity to how small an interaction rate I can look for. And hopefully, eventually, we will figure out that dark matter does interact. And then you discover something more than that. So just to complete my analogy about atmospheric air, you see, for a while inert gases like argon were thought to be inert. But we know that we can ionize inert gases by applying voltage, right? And now you can go and look for the excitation lines of argon by just doing air discharge.
and the energy levels of argon basically tell you the orbital energies for fully filled shell. And basically, if you think about it, before quantum mechanics came about and we understood the deep fundamental physics that leads to the periodic table of elements, in a certain sense, chemistry, which set up this periodic table for us, set up like the crude playground that forced us to think about atomic physics in terms of chemistry. And the fact that 2, 8, 18 and so on, these are interesting numbers, told us something about the solution to the hydrogen atom problem, which eventually, underlying all of that is quantum mechanics, which was this big discovery in the 1920s. What dark matter could do for us is very similar. So we have some current theory of matter, standard model. But we have this form of matter that doesn't fit within the standard model, which is like this inert gas. Understanding the microphysics, the chemistry of dark matter, in principle could tell us about how matter needs to be organized in a periodic table, like the periodic table for chemistry, and discover the 18th column for the standard model, which would tell us new organizing principles, which would tell us something more fundamental about the nature of matter. Okay? That's the reason why we are excited about discovering the nature of matter.
In a possible likely scenario, would it not have cosmological imprints and would it not modify this curve that you see from Planck and all that?
Yeah, so one has to compute these things and people have done it. So it turns out that for most of these asymmetric dark matter models that I talked about, all this annihilation and all of this happens so early enough in the universe that the subsequent CMB and last scale structure, all of these things are preserved. Like basically it behaves like cold dark matter.
Okay, so it happens much earlier than the surface of last scatter, say, both pehle.
So basically all of this dark matter physics happens at GeV scales, and all of this is happening at electron volt scales and below. So you don't get anything.
So there are no cosmological imprints of
Asymmetric dark matter?
because the structure formations and all that, so much of energy is released into some particles, then it
But
would
this was released long ago, and all of that energy has thermalized into photons. If everything was in equilibrium earlier in the universe, so in equilibrium, once you're in equilibrium, it doesn't matter how you got to equilibrium.
It erases the previous.
It erases all. So that's what. So okay, I should not say that there are no consequences of being asymmetric dark matter. I'm sure one can think of something, but there's nothing like that's really compelling. I'm not aware of a smoking gun test for asymmetric dark matter using cosmological observations.
So, sir, actually regarding the point where we talked about neutron stars, so I just had a curiosity that do we, when we check for neutron stars in our experiments for black matter, dark matter, do we look at pulsars in general more because it's easier to detect in general, or just normal neutron stars is more used in the experiment?
I didn't put
As in,
repeat that one more.
Yeah, sorry. To better frame it, I would say that our pulsars looked at more often for our experiment because they're easier to detect in the universe due to the thing. But then at the same time, I feel that since pulsars are so incredibly fastly spinning, it will be harder to conduct the experiment of black matter due to its certain. I mean, it will complicate certain stuff. I feel. So do we look at more pulsars or normal neutron stars for our experiment? Is what I mean.
So radio observations pick up mostly pulsars. But gravitational wave detectors pick up neutron stars which may or may not be spinning. Neutron star mergers or neutron star black hole mergers. Gravitational wave detectors I don't think care too much about the spin of the neutron star. I imagine that there are also astrophysical ways of looking for neutron stars beyond just radio astronomy, which only gets things from pulsars. So there are ways of detecting non-spinning neutron stars, but it's hard.
Yeah,
it's significantly harder. So your sample is biased. You are mostly detecting pulsars. That's true. But that being said, what I told you about the dark matter accretion onto a neutron star
That doesn't really depend on whether the neutron star is spinning or not.
I see. Okay, so our experiment doesn't get any harder depending
I
on
don't
the
think so. I mean,
Yeah, actually, first thing is excellent talk. Okay, so yeah. So just exactly I want to just pick up from there. What happened that suppose if I just consider pulsar only, and then little bit of even that asymmetric accumulation of dark matter on the pulsar is completely changed the profile modulation.
that's right.
And that is actually very precise.
That's right.
Actually this one.
That's
In
right.
fact, that is better than any kind of disappearance
right.
of completely.
This has been done. This was one of the things that we wanted to do, but then we realized that that has already been done. So the idea here is that,
And it's also gravitational addition of the
absolutely right. Yeah. So there's a neutron star that's spinning. So this is a pulsar, and these are clocks. These are incredibly precise clocks because the radiation from this pulsar points to this thing that's spinning like this, and every time the axis points towards you, you get a burst of radiation, and so this, from your perspective, looks like a very consistent pulsing. So that's why pulsar. Now, this rate at which these pulses come, this is very consistent because there's a rotation period, but it's not exactly constant. The rate decreases over time because as this thing is rotating like this, it loses energy in gravitational waves. This was discovered long ago.
But decay is very small.
Very, very small. So I'm coming to that. So there's something, there was something called the Hudson-Taylor pulsar, and so that's very well measured, and you could then see that the pulses, successive pulses, are getting farther apart, but this effect is incredibly tiny. It's an incredibly tiny effect. You have to be very precise, and that's how we first discovered that there must be gravitational waves. Now, what the idea here is that if there is accumulation of dark matter into the pulsar, that will change the moment of inertia of the pulsar essentially. And so how it spins.
Not only that, it's an asymmetric moment of inertia.
So there are complications. Assuming that for simplicity, let's assume that the dark matter accretion is symmetric. So it doesn't make it wobble or anything. Even then, the moment of inertia changes, for example, and once the dark matter is accreted, the profile of the matter inside the star also changes. But nevertheless, all of this will change how the pulsar spins down. And you could look for that, and people have come back, people have used that to their bounds.
I have one related question to that, but it can also changes the emission properties of the neutron star in some sense, like the things that is going out.
So tell me more, why?
Because now there is, in addition to the dynamic matter, we have the electricity.
Tiny amount, very small amount at the center. Like 10 power minus 8 solar masses in a 1 solar mass star. So one should look at it, and I would love to know more, but my intuition suggests that the small amount of dark matter that I am talking about doesn't necessarily give you any change to the way the star burns, essentially. Or in any case, neutron stars are there, right? They don't do anything.
There is a sort of a transition, right? Because it accumulates and then it becomes a black hole. So you might see some changes.
That's what, so again, would love to, talk more about it. In fact, to be honest, I have been talking to somebody who's an expert in these areas. We have some calculations. For example, we've computed the Tolman for 30 of equations.
That would change, right? But
it doesn't change much. So unless the mass of the dark matter accreted reaches about 1% of the neutron star, basically the signals all stay within less than 1% of whatever they used to be. So the changes are essentially proportional to the ratio of dark matter mass to the dynamic mass. And because once that is small, all the changes are tiny. But of course, if you have some other theory in mind, not my theory, but something else in mind, that this is some dark matter or something which is accumulating into the neutron star, and maybe it's 30% in this case or 10%, and you would have large effects. And you could try to ask what are those effects and what do they look like. But that's a different question.
Just kind of towards when we talk about this dark matter interacting with the neutron star inside and then losing energy to coalesce inside the black this collision with the stuff already inside your matter. How are you modeling that dark matter and normal matter?
How are you modeling?
Yeah, because you talk about this classical mechanics losing energy. Right? When we study this in front of classical mechanics, we say, okay, this is because electromagnetic induction, electron-pulsar carrying each other. That clearly can't happen with that. If we move on to the second explanation, which is Pauli-Solution principle, then that should also eliminate a bunch of, like for example, primordial black holes should not be moving. Right? Because they are not a subatomic particle type of stuff where Pauli-Solution principle should occur.
Sorry, I don't get it.
So the idea is when you say these dark matter collide with the matter inside neutron stars, right? This collision, what type of physical processes is happening in this collision? What is mediating this? It's some sort of can't be electromagnetic, right?
Yeah. So, but let's not think in terms of such small microscopic details. Think in terms of what I would call mesoscopic details. So think in terms of there's some cross section. There's some rate that depends on cross section. When I, let's say, tell you that I have two balls, billiard balls or cricket balls, and I throw them at each other, what is the cross section? The cross section is 4 times pi times the diameter of a ball square, right? Did I really need to know that these balls interact using electromagnetism? I mean, I know that they do, but do I need to know that? No. I can compute the cross section even without knowing. Suppose I don't know anything about Maxwell's equations. I don't know any Maxwell's equations.
But if you didn't know two billiard balls interacted at all, then you can just as easily expect they don't collide.
Correct. So I am not predicting the cross section, if you notice. I am simply saying that let there be a cross section, and I am asking from observations how large a cross section can I tolerate. So you see, this is a different approach. So this is not a very particle physicsy approach where I say that, see, I have a very clever model for dark matter, and I tell you that this must be the cross section. I am not quite that brave or ambitious. My approach here is very humble. I say that, see, I know that experimentalists are very smart. They have built all these instruments which can look for things. Let me only assume that there is some cross section. I don't know where it comes from, I don't know how large it is. But then I am going to show you using experimental data what cross sections I can look for and what that tells us about a variety of models. So you got the problem around.
Can we use gravity as the lower bound to set that cross section?
That is true, yes, for sure. Yes. But that's really small. Right? That is incredibly small.
By detecting the dark matter, more specifically electric. So what observable we are actually looking for is like equal energy, like if you consider the ball and then equal energy. So is this energy is a correct observable here by detecting the dark matter, or we can mention any other observable like any quantum scale?
I don't know if I fully understood your question. I think you are asking that when dark matter comes and collides with ordinary matter in my direct detection experiment, the ordinary matter, let's say something like this, recoils. I am measuring the recoil energy. This is usually done by either seeing how the matter heats up, because this recoil energy is lost as heat, or because it ionizes particles and you see ionization, or sometimes it can ionization, there is thermal, there is also I think some circulation in some cases, or so there are a bunch of techniques. So for example, there are cases where you make a bubble and then you try to measure the sound created by that bubble colliding and so on. But you're right, basically we are measuring the energy of this recoil particle. I am not sure what else I could do. I mean, in a certain way, once the dark matter particle has interacted, I think the only thing that so I don't then need to know anything about dark matter. Now I only care about what are the properties of ordinary matter that I could be looking for. And that is just energy momentum. What else do I have?
Till now we are just measuring the classical signals. Till now we are just measuring the classical signals.
You are going very okay. I see. That's a great idea. Yes, in is a great idea, by the way. So, okay, so this is a half-baked idea that I will tell you about. So, okay. Okay, I don't want to take too much time, but very quick answer. Yes, if you could create a detector, a substrate, that was very special in the sense that imagine that there are a bunch of spins that are all entangled with each other. So let's say in some state where you can't just move one spin down just like that. All the spins are in a certain angle. Then actually you could create situations where this incoming particle would coherently interact with all of these particles and you would be much more sensitive. Now, to an extent, this is already being done in their detection experiments because all the nucleons inside a nucleus, so let's say xenon, it has an order 100 neutrons, protons, whatever inside a nucleus. For spin independent detection, you do kind of use quantum coherence idea to boost your detection rate by a factor of 100 square. Because the amplitude goes as the number of targets and then the probability goes as amplitude square, 100 square is 10,000. So you actually are already benefiting from your quantum coherence in these direct detection experiments. But you could definitely think of similar ideas not involving nucleons, but involving, let's say, qubits, and try to build new kind of dark matter detectors. This is a very nascent field, though there are people working on it even in India. Yeah, but I don't know very much about it.
We are short of time. We'll take just one last question and then you can always catch Basudeb.
Yeah, I'm here until whatever, day after early morning.
Last question.
So in these symmetric dark matter this in the high energy universe that electron proton pair could create dark matter pair, right? So what are the general evaluations in this it can happen?
We don't know. So that's a short, very easy to answer this. We don't know.
So if we know that the dark matter doesn't interact with itself per se,
okay,
using this theory. And we know that since let's say the symmetric dark matter hypothesis is somewhat big, so we already have spin conservation, then we do a sort of electron proton interaction. Let's say the spin of the said dark matter particle is say 0, right? So can we assume that it can be a massive boson field because statistically on the side of statistical mechanics, it makes more sense to have non-interacting boson just passing through each other instead of say fermions because they would have some interaction.
Yeah, all of these are good questions, and there are in various ways these kind of questions have been asked and not constantly being asked. But to kind of zoom out a little bit and maybe give you a bigger picture on the question that you're asking that does the spin and the boson fermion nature of the particles, dark matter, the other standard particles they annihilate into or are created from, does this have an important role to play in how we learn more about the features of dark matter? And the answer is absolutely yes. So this is something that is a very important part of what I would call particle physics. In fact, maybe this is a good opportunity for me to say this, that the field of astroparticle physics is very poorly understood, not just in our country but across the world, because by its very nature, it is a moving boundary. My definition of astroparticle physics is that it is the boundary at which we use frontier fundamental physics rules. That frontier was quantum mechanics in 30s and 40s and 50s, and became nuclear physics in 1960s and 70s, and is now kind of modeled basic law of particle physics. And you apply these fundamental rules to frontier observations in astrophysics. What happens over time is that what used to be frontier particle physics or quantum mechanics becomes routine things that even astronomers and astrophysicists learn and know. At that point, let's say you are just doing atomic physics in a star, that's neatly astroparticle physics, but not quite. So the real astroparticle physics is in being able to take really the frontier topics in each of these areas and be able to work across. Use both languages. Eventually the fields catch up, and there is no novelty in telling some astronomer about quantum mechanics because they also know it. In 1930s, if you told an astronomer, let's say about atomic physics, Baumol lines or whatever, then or you told them in 1940s about renormalization and the fact that I can measure the magnetic moment or whatever and I can calculate it, that would be new. Today, you have to do different things. So in fact, the kind of question that you are asking about using the detailed structure of particle physics to extract more information in astrophysical context, that is precisely the novelty and the heart or whatever, to use these precise things. Thanks for that question.
Yeah, I think we can thank Basu for the wonderful talk.